we can do some numericals. First question, a rectangular loop of side 25 cm and 10 cm carrying a current of 15 ampere is placed with its longer side parallel to a long straight conductor 2 cm apart carrying 25 ampere. Find the net force on the loop. Figure is also given. So, this is a rectangular loop ABCD, sides 25 cm and 10 cm, and it is placed parallel to another conductor carrying 25 ampere, and the distance is 2 cm. Okay. Now, we have to find out the net force on the loop. Here, what is the force on the side AB? Here, this AB and XY, this is a straight conductor placed. So, AB and XY, there is a force between AB and XY. These two are parallel conductors and the currents are also flowing in the same direction. And we know that parallel currents attract, isn't it? So, the force acting on side AB, so that is the first one, force on side AB. Force on side AB is, let it be F1. And we know the force between two parallel conductors is given by the formula mu 0 I1 I2 L divided by 2 pi d. This is the general formula, isn't it? Now, here we can substitute F1 equal to mu 0 into what is I1? I1 the current 15 ampere and 25 ampere, no? So, one 15 ampere and another one 25 ampere into L. What is the length? This length is equal to 25 centimeter. So, 25 centimeter convert to meter, 10 raised to minus 2. Okay. Divided by 2 pi into d. What is the separation between them? 2 centimeter. So, 2 into 10 raised to minus 2. Clear? So, force between AB and XY. Force acting on the side AB. We can substitute the value of mu 0 also. So, 4 pi into 10 raised to minus 7 into 15 into 25 into 25 into 10 raised to minus 2, the whole divided by 2 pi into 2 into 10 raised to minus 2. Okay. After simplification, we will get the answer as 9.375 into 10 raised to minus 4 Newton. So, that is the force acting on the side AB. Now, what is the direction of that force? We know that parallel conductors always attract. So, the direction of force acting on the side AB is towards. This is the direction of F1. Clear? Now, we can find out the force acting on the side CD. So, next one is force on side CD. Again same formula, that is given by F2 equal to same formula mu 0 I1 I2 L divided by 2 pi d. We can substitute mu 0 means 4 pi into 10 raised to minus 7, I1 is 25 into 15 ampere, L is same 25 centimeter 10 raised to minus 2 centimeter convert to meter divided by 2 pi into d. Force acting on CD, due to this external conductor XY and CD there is a force. Okay, so what is the force acting on CD? Formula we have taken and substitute the value. And what is the distance between CD and XY? This is 10 centimeter. Here it is 2 centimeter. So what is the total distance? 12 into 10 raised to minus 2. Okay. And after simplification, you will get the answer as 1.5625 into 10 raised to minus 4 Newton. Okay, so that is the force acting on CD due to this conductor XY. And what is the direction of that force? We can complete the figure. This is in this direction. Here the current is in this direction. Here current is towards left. And here current is in the downward direction. So what is the direction of current between CD and XY? They are anti-parallel, no? CD and XY, the currents are in anti-parallel direction, opposite direction. We know that anti-parallel currents always repel. Now what is the direction of force acting on CD due to this XY? They repels. That means in outward direction. This is the direction of F2. So F1 is towards one direction and F2 is in the other direction. So what is the net force acting on the side ABCD? We can subtract, isn't it? So net force on ABCD or the loop, net force on the loop is given by is F1 minus F2, since they are in the opposite direction, is equal to, we can subtract 9.375 into 10 raised to minus 4 minus 1.5625 into 10 raised to minus 4, and its value is 7.8125 into 10 raised to minus 4 Newton. So this is the net force acting on the loop. And what will be the direction? So since F1 is greater, no? So the net force is towards in the direction of F1. That means the direction of F1 is in the downward direction towards the conductor XY. So here net force is also towards the conductor XY. So direction is towards the conductor XY. Clear? Suppose a helical spring is suspended from the roof of a room and a very small weight is attached to its lower end. What will happen to the spring when a current is passed through it? Give reason. So helical spring is suspended like this. This is a helical spring. This is suspended like this, and a small weight is attached at the other end. Clear? And the circuit is connected. It is connected to the battery and everything. Okay, and if current passes through the spring, what happens? That is the question. So what happens? We know that in a helical spring, through the adjacent turns of the coil, current is flowing the same direction, isn't it? So when current is passed through the spring, it will flow in the adjacent turns of the spring in the same direction. And we know that parallel currents always attract, and hence what happens to the spring? The spring contracts and this weight will be moving up. So that is the answer. So when current passed through the spring, it will flow in the adjacent turns in same direction, and since parallel currents attract, the spring will contract and the weight will be lifted up. Now next numerical, a solenoid 50 cm long has 4 layers of windings of 350 turns each. The radius of the lower layer is 1.4 cm. If the current carried is 6 ampere, calculate the magnitude of magnetic field near the center of the solenoid, outside the solenoid, near its center, near its ends on its axis. Okay, so we know it says what is a solenoid? Insulated copper wire wound in the form of a cylinder or helix, that is called a solenoid. Okay, so here this solenoid having length 50 centimeter. So length of the solenoid is equal to 50 centimeter. You can convert to meter. 50 into 10 raised to minus 2 meter. Number of turns 350 turns. So how many layers are there? 4 layers. So one layer having 350 turns. So what is the total number of turns? 350 into 4. Okay. So total number of turns is equal to 350 into 4. Now radius of the lower layer is 1.4. So radius are equal to 1.4. Again we can convert to meter. Current I is given as 6 ampere. Right. Now we have to calculate the magnetic field near the center of the solenoid. So what is the magnetic field inside the solenoid? So first one, magnetic field inside the solenoid is given by B equal to, what is the magnetic field inside the solenoid? B equal to mu 0 Ni. Okay, so that is the magnetic field inside a current carrying solenoid is equal to, what is the small n? Total number of turns divided by length, that also we know. So it is equal to mu 0, small n is capital N divided by n. Small n is capital N by n is equal to, we can substitute 4 pi into 10 raised to minus 7 into n. What is n? 350 into 4 into current. What is the current given? 6 divided by length. What is the length given? 50 into 10 raised to minus 2. Okay, so a radius, the value of radius is not needed here, is equal to, we can substitute. So we will get the answer as 2.1 into 10 raised to minus 2 Tesla. That is the magnetic field inside the solenoid. Then number 2, magnetic field outside the solenoid near its ends. So from the derivation, from the second application of Ampere's circuital law, we have derived the magnetic field outside the solenoid. What is the magnetic field outside the solenoid? Magnetic field outside the solenoid is 0. Okay. So magnetic field outside the solenoid near its center is 0. Then number 3. Magnetic field near its ends on its axis. That means this is a solenoid. Magnetic field at the ends, near its ends on the axis. On the axis of the solenoid near its ends, what is the magnetic field? Magnetic field is given by the formula B equal to mu 0 Ni divided by 2. So magnetic field inside is mu 0 Ni and the magnetic field outside the solenoid near its ends, on the axis near its ends is mu 0 Ni divided by 2. Okay. So that is mu 0 Ni, we know it is 2.1 into 10 raised to minus 2 divided by 2. Okay. So it is 1.05 into 10 raised to minus 2 Tesla. That is the magnetic field near its ends on its axis. Okay children. Toroid has a core of inner radius 20 cm and outer radius 22 cm around which 4200 turns of a wire are wound. If the current in the wire is 10 ampere, what is the magnetic field inside the core of the toroid and outside the toroid? Okay, we know what is a toroid. A solenoid bent in the form of a circle, that is called a toroid. So here you can consider a ring over which wires are uniformly wound. Okay children, so that is called a toroid. So here the inner radius, this is a toroid having inner radius, this is the toroid that you know. Okay, so here current is entering and here the current is leaving. So inner radius is given as, what is this inner radius? That is equal to 20 centimeter and outer radius is equal to 22 centimeter. Magnetic field B equal to mu 0 Ni divided by 2 pi r. That is the magnetic field in the inner core of the solenoid. So B equal to mu 0 Ni divided by 2 pi r. Here N is given. What is the number of turns given? 4200 turns. Current I equal to 10 ampere, right. Radius, inner radius and outer radius are given. We have to find out which radius the mean radius we have to find out. Okay, so 22 outer radius, 20 inner radius. So what is the mean radius? 20 plus 22 divided by 2, that is equal to 21 centimeter is the mean radius. We can convert to meter. Okay. Now all the values are given, we can just substitute B equal to mu 0 4 pi into 10 raised to minus 7 into number of turns 4200, current is 10 ampere divided by 2 pi r. What is the radius? 21 into 10 raised to minus 2. After simplification, you will get the answer as 0.04 Tesla. That is the magnetic field in the inner core of the toroid. Okay, inside the core of the toroid. Here only magnetic field exists and the magnetic field within the core of the toroid is B equal to mu 0 Ni by 2 pi r and substituting the value you will get the answer as 0.04 Tesla. Then what is the magnetic field outside the toroid? Magnetic field outside the toroid, we know that magnetic field is 0. So outside the toroid magnetic field is equal to 0. Okay, magnetic field in the inner region here, in the inner space is also 0, outer space is 0 and magnetic field exists only within the core of the toroid.